All right, this is Le Chatelier's principle part two. Last time we were talking about what would happen with this equation here if we increase the pressure of the container by, in this case, pressing the piston down and decreasing the volume. So we're talking about pressure increases by volume reduction. And for this reaction, we talked about it in terms of pressure, and the pressure of B is to the second power because for every one A we get two B's, and then we have that over the pressure of A. We also explained it in terms of if R and T are held constant, and P equals nRT, then we can think of pressure in terms of number of moles over volume. So it'd be number of moles over volume squared for B and number of moles over volume for A. And the question is, if I increase the pressure by decreasing the volume, what happens to these two terms? Well, this term's going to get larger. B is going to be larger than A. And so overall, we're not at equilibrium. This is incorrect here. Overall, we're not at equilibrium, and so Q, the reaction quotient, is what we use. Q would be greater than K. And again, the reason why this number is going to be larger, because it's squared. For every change in volume, we're going to get number of moles squared, volume squared. This term is going to change more drastically than this term. All right, so Q will be greater than K. So in order for this reaction to relieve the stress of increasing the pressure by decreasing the volume, the reaction is going to have to shift back to the product. Back to the reactant. And the reason why is, again, you've got all this B, and this is changed more so. And an easy way to think of it is, the more B that's formed, the higher the pressure. So that pressure has to be relieved, and so as B reverts back to A, we go from two particles inside this volume to one particle. So we see a reduction of 2 to 1 as the product goes back to the reactants. So mathematically, this is how we prove it, but you can think of it intuitively that, as one particle forms two particles, pressure normally would go up, and so if we go from two particles back to one, the pressure should decrease to get us back to equilibrium. Now, the other thing we could think about here is what happens if we move the pressure. We go from here and we move the piston up to here, which represents, this is just a symbolic representation of pressure. So we're going from here back up to here. So we are decreasing the pressure, and by decreasing the pressure, we're doing that by increasing the volume from here to here. So there's a change in volume, a plus change in volume here. What happens to the reaction? Well, in this case, volume's getting larger, and volume is getting larger here, and we have number of moles divided by volume, which is a larger quantity. That's going to make this numerator smaller than the denominator, because it's being affected squared, whereas this volume is only being a squared proportional, 1 to 1, right? So Q then becomes, for this reaction, Q would become less than K, and so this reaction would shift in a forward direction. Let's just rewrite it. So this reaction would shift in a forward direction to get B back up to an A, decrease of A and increase of B to get the reaction quotient equal to K. All right. So what I would suggest is to look at this relationship here and see how a reduction in volume is going to make this term larger because we've got a number that's fixed. The moles are fixed. This gets to be smaller. That makes this term overall larger than this term will be. Especially this is squared, right? So it's affecting this more so. So Q is greater than K in this instance, and the reaction goes in reverse to reduce the amount of pressure back to by going from 2 particles to 1, if you want to think of it that way. Down here, we increase the volume. What happens is Q will be less than K because as we increase the volume, this number becomes larger, this overall term becomes smaller, and this becomes a ratio smaller than what the original equilibrium constant was. And so the reaction shifts to make up for that difference by increasing B and decreasing A till we get back to the equilibrium constant. All right, let's look at another example dealing with pressure. Let me get the pen again. I can see it's dropped out. So we're still talking about A going to 2B, and I do sometimes forget to put the double-headed arrows. So again, we're trying to say this process is reversible. And again, if we're looking at the equilibrium constant in terms of pressure, it'd be the pressure of B squared over the pressure of A. And again, I think it's important to think about it in terms of number of moles divided by volume squared divided by number of moles over volume with respect to A and with respect to B. All right, so here's the next scenario. You have your cylinder, you have a certain pressure, so here's our pressure symbolized by this piston. Now, instead of decreasing the volume, we're going to inject another gas like helium, an inert gas like helium that does not react with either reactant A or product B. We're going to inject helium into the cylinder. So what's going to happen to the pressure? Well, the pressure is going to rise. You've got more particles in that particular volume. They're going to strike, if we have a pressure gauge here, they're striking the diaphragm of the gauge more frequently, and we see that as an increase in pressure. How does that affect the equilibrium? Does it affect the number of moles of B or the number of moles of A that's in here? Is the volume changed? No, the volume hasn't changed because remember, when we look at gas particles, there's a lot of empty space between them. The cylinder's not moving, so the volume is not changing. So in this case, when we add an inert gas, a gas that does not react with reactant A or product B, there's no effect on equilibrium. So if we are at equilibrium and we add this inert gas, we see no change. So this is important. Sometimes we want to add an extra gas, maybe to decrease the possibility of an explosive reaction or something like that. So we'll add an inert gas. Has no effect on equilibrium. How do you know? What's a good way to know that this doesn't have any effect? Well, you have to look at the gas and see, would it react with A or B? And in a general, this is a general equation, but in a specific equation, you'll have to think about, does this gas react with either the reactant or the product? And second of all, look at your expression. The only two players here in this reaction is B and A. There's no pressure for helium anywhere in this expression. So if it's not in the expression and it doesn't react with any of these substances that's in the expression or in the balanced chemical equation, then it's going to have no effect on equilibrium.